Well, thank you everyone for coming for our next seminar on probability stochastic process in USP. This week we have Mariela Penton Machado. She did her master at IMPA and her PhD at Federal University of Rio de Janeiro. And she has been working with metastability in contact process, and she's gonna speak a little bit about for us. Thank you, Mariela, for accepting the invitation, and welcome to you.
Thank you for the invitation, and I'm going to speak about the contact process. And about the contact process, I'm going to speak about the two-type contact process, and I want to study the set of invariant measures of this stochastic process. So, sorry. This is the outline of my talk. I'm going to give a brief introduction with the definition of the classic contact process and the two-type contact process. After that, I give the statements of my results, my two main results. And before I give the sketch of the proof of these main results, I need to present the Mumford-Sweet renormalization, because this is an important tool for the results, for the proof of the results. Okay, the contact process is a widely studied stochastic process. It can be interpreted as the evolution of a population or an infection. It was introduced in this paper of Ted Harris in 1974. And I want to study the two-type contact process. The two-type contact process, a version of the two-type contact process appears the first time that appears is in this paper of Durrett and Swindler in 1991. What happened in the two-type contact process? You are in the presence of a contact process that has two types of particles, and in this case, in this paper, the particles of type 1, you have two types of particles, 1 and 2, and the particles of type 1 have priority in all the environment. That's the process that they studied in this article. Okay. The definition of the contact process, of the classic contact process, is the following. I need to explain the Harris construction. Well, before, I'm going to say that I'm going to in all the talk we're dealing with the contact process with finite range, and R is the range, and we are in the supercritical case. The contact process presents a phase transition in the rate of infection. Lambda is the rate of infection for the contact process. And what does this mean? This means that if we take lambda smaller than lambda c, a finite fixed number, there exists only one invariant measure for the process, the trivial invariant measure. But if we take lambda larger than lambda c, then we have two invariant measures for the process, the trivial invariant measures and a non-trivial invariant measure that we denote by mu. Okay. In all the talk, we are in the case when we have we have a non-trivial invariant measure for the contact process. This is the supercritical case. Okay, to define the contact process, we need to take for every x in Z, we take a Poisson point process for this point, for these sides x, and we take another Poisson point process for every neighbor of x. resides y that is a distance smaller than r, the range of the contact process. All these Poisson point processes are independent, and these have rate 1, and all these Poisson point processes have rate lambda. Okay. In the line x, suppose this is x, in the line x time 0 to infinite, we, for every realization of this Poisson point process, we draw a cross mark like this, for example. And for every realization of this point, if we take, suppose this is y, then for any realization of this Poisson process, we draw an arrow coming out from the line of x and going to the line of y. Then we have all these marks. These marks are the Harris construction, and we define what is a path in the Harris construction. The path will be an union of intervals of time that do not have cross, and together with arrows. For example, here we have a path. Here we have another path, and we stop in the cross, and so on. Then if we begin with these 3 points at time 0, and this is time t, all the points that has a path that begins in these 3 points are infected at time t. And that's the definition of the classic contact process. And this is the notation that we use when the initial configuration of occupied points, infected points, are A. Then the two-type contact process. The two-type contact process is the following. We have the same Harris construction, but also we have, in a deterministic way, we know which sites like which type of particles. For example, suppose here I say that these sites likes blue particles. Blue particles, I have to say that blue will be in correspondence to type 1, and red, no. And red will be in correspondence of type 2. Sorry. Type 2. Okay. Okay, then in a deterministic way says that these sites here likes blue, these sites here likes red, this one likes red also, this like, it doesn't matter, blue, this like blue, and this red, and this red. Okay. Then all the interaction is like the classic contact process, except that if like here, if these sites likes the particles of type 2, the red particles, then if an arrow comes from a particles that is occupied by particles of type 2, then it will change no matter if it is occupied by a particle of type 1, it will change to a particles of type 2. And in the same case, in a symmetric case, if we are in a site that likes particles of type 1, and arrows come from a particles a site that is occupied by particles of type 1, then it will be occupied by particles of type 1. The other interactions are the same as the contact process, and we will use this notation for the two-type contact process when the initial configurations of particles of type 1 are A and the initial configuration of particles of type 2 are B. And we work with this deterministic priority. The particles of type 1 have priority in -infinity to 0, and the particles of type 2 have priority in 1 to infinity. That's the definition of the two-type contact process. And about this process, we prove the following results. First, if we take this process, Z intercept, this is the two-type contact process when in each side of Z, we begin with the particles of type 1, and there are no particles of type 2. Then this is the classic contact process. And since we are in the supercritical case, this converges to μ1, to a measure μ1 that basically is a non-trivial invariant measure for the classic contact process. If we take this process, intercept and Z, this converges to another measure. This process is, I'm beginning with every site in Z occupied by particles of type 2, and there are no particles of type 1. The interaction, since it's the same as the classic contact process, it behaves as a usual contact process, but in a 0, 2 to the Z, the configurations here. Then this measure will be essential the non-trivial invariant measure for the classic contact process, but supported in the configuration that don't have particles of type 1. Well, the first theorem says that okay, this process is the two-type contact process with initial configuration, all sites occupied by particles of type 1 in -infinity to 0, and all sites occupied in 1 to infinite by particles of type 2. That's the notation that we use. Then this theorem says that this process converges to nu, and this nu is different, it's a non-trivial invariant measure for the two-type contact process, but it is different from μ1 and μ2. This is the first theorem. The second theorem is the following. Every invariant measure for the two-type contact process is a convex combination of these four measures. So the external points for the set of invariant measures is these four measures. Okay. Well, before the sketch of the proof of these theorems, I'm going to define the Mumford-Swift renormalization. The Mumford-Swift renormalization is a K-dependent oriented percolation system, and for each pair Mn such that the sum is even, we will associate a renormalized box like this. This renormalized box has an interval in the base, and the intervals in the base is centered in this point that depends on M and N. The numbers had N and had K are constants. And another thing in this renormalized box is that we have a thin rectangle in the middle. I have a picture of the dimensions of this box. We have this box have a length in the base that is hat n. The height is hat k and hat n. Hat k by hat n, And the width of the rectangle in the middle is 2r. R is the range of the contact process. This is an important detail in the construction. Okay. The man-for-suite renormalization is it's a random object in 0, 1, 2 lambda. Then we will set lambda in Mn equal 1 if we have 4 properties that I'm going to explain. Otherwise, we set 0. First property first condition that we need to set PC in Mn equal 1. The first condition is that we need that in the top of this renormalized box is the ones associated to the point Mn. And we need that in the top of the renormalized box, there are a lot of points that are connected in the Harris graph with z times 0. A lot of points, more specifically, is that for each interval in the top of the renormalized box of length square heart n, we need there must be at least one point that is connected in the Harris graph with z times 0. This is the first condition. The second condition is that if we have a point in the top of the renormalized box that is connected in the Harris graph with z times 0, then this point is connected with the base of the renormalized box. It's connected in the Harris graph with the base of the renormalized box. Third condition is the same, but for the rectangle in the middle. If we have any point here that is connected in the Harris graph with z times 0, we need that this point is connected with the base of the renormalized box. Finally, the fourth condition is that every path that has at the end has a point in the renormalized box is inside. Every path that has a point that ends in a point in the top of the renormalized box or in a point that is in the rectangle in the middle must be inside of a rectangle that depends on hat k and hat n, but the dimensions of these rectangles are constants depending on hat k and hat n. I don't know if I was clear. It's every path that connect a point in the top of the renormalized box and to the base of the renormalized box, and the same with the rectangle in the middle. All these paths are in the middle or in the middle are inside of a larger rectangle that has dimension constant. Okay. This is the man-for-suite renormalization presented in 2000. And for this K-dependent percolation system, we have this lemma. For every epsilon larger than 0, we can find hat k and hat n such that with probability larger than 1 minus epsilon, our construction is in the following set. I'm explaining better this set in the next slide. This and here I must to write here that this is for every n. We have this statement for every n. Then for every n, what we want this event is the following. There are an open path in percolation to the right of this line, and this path ends in this point. The important thing in this point is that E is bounded by 2. Then it's or 0 or 2 or 1, depending on n. And what else? That's the thing. Then our construction must has an open path to the right of this line. The important thing in this line is that has negative inclination, and we have this for every n, smaller n. Okay. With this lemma, we prove the following proposition. This proposition says that for every epsilon larger than 0, there exists an m such that with probability larger than 1 minus epsilon, this notation means that the rightmost particle sites occupied by a particle of type 1 is to the left of m. This is the rightmost sites occupied by a particle of type 1 for this process, the process with full occupancy in the favorable environment for each particle. And in this event, we have that the leftmost sites occupied by a particle of type 2 is to the left of minus m. Okay, that's the statement of the proposition, and this proposition it's a consequence of the lemma 1, because by lemma 1 we have with probability larger than 1 minus epsilon, we have this structure for the Manford-Sweet renormalization. This is a path in the Manford-Sweet renormalization with each box open. Each of these boxes satisfies the 4 properties. Okay, then what happened with this structure? If we take a point to the right of this structure, there are 2 possibilities. Or there exists a path that is always to the right of the structure, Rn, sorry. And if there exists a path that is always to the right of Rn, then we are connecting a site that is occupied by particles of type 2 to these sites using a path that is always in the favorable environment for the particles of type 2. Since the particles of type 2, when they are in the favorable environment, this means the particles of type 1, then all this path is red. Yes? And the other case is that, as in the picture, there are no such path always to the right of Rn, but there are a path that begins in the blue part and ends in these points. But if this happens, this path must cut the structure Rn, and once it cuts the structure, since all these boxes are open, we can construct a path here using the boxes, and when we have a path that is always in the favorable environments for the particles of type 2 and begins in particles of type 2, then we also are constructing a path that is always red. And these particles has a particles of particles of type 2, and this happens for any size that is to the right of the structure. And we can construct the same thing. We can construct a blue structure here using a lemma 2. We can construct the same thing here, and so on. And we will understand that there are no particles of type red to the left of minus m. Okay, that's the proof of the proposition. With this proposition, we gain the existence of an invariant measure that is different from μ1 and μ2, because we have, suppose, these are the configuration that has infinite particles of type 1 in minus infinite to 0, and infinite particles of type 2 in 1 to infinite. This corollary is a consequence of the proposition, and I'm not going to enter in the details, but what we have is that there exists an invariant measure that is supported in this set of configurations. The configuration that have infinite particles of type 1 in minus infinite to 0, and infinite particles of type 2 in 1 to infinite, and therefore nu must be different of μ1 and μ2, because these measures are supported in the configuration that only have one type of particles. Okay. Then we have a nu, the existence of a different nu. To prove Theorem 1 and Theorem 2 also, we need a technical proposition. And for this proposition, I use the definition of expanding to the right. Expanding to the right is a definition that is given by Angel, Manford, Pimentel, and Valesin. And I'm going to define what is expanding to the right. Expanding to the right or to the left. For both definitions, I will say that a point is expanding to the right if we have two conditions. The first condition is that we take the point xt, and for the point xt, we take the renormalized box in the Manford renormalization that contains xt, and we associate the pair ik for this renormalized box. And I'm going to, we need that this point is connected with any point, with all the points in the top of the renormalized box. That's the first condition. This condition is the same for expanding to the right or expanding to the left. The second condition is the difference. Then in the second condition, for expanding to the right, I need, once we have this renormalized box that contains the point xt, we want that there exists an infinite path in the percolation system that is always to the right of a line, this line. Then in the Manford renormalization, in the Manford renormalization, we want an infinite path that begins in the renormalized box that contains xt, and this infinite path is always to the right of this line. The important thing is that this line has a positive inclination. For expanding to the left, the first condition is the same. I want that everything is connected here with xt inside the renormalized box, and I need an infinite path in the percolation in the Manford renormalization that is always to the left of a line that has negative inclination. Okay, this is the definition of expanding to the right or to the left, and what they prove is that with probability larger than a constant, 0, 0 is expanding to the right. And since it's symmetric, all the construction, then 0, 0 is expanding to the left, the probability that 0, 0 is expanding to a left is also larger than a constant positive. Okay. Then my technical proposition to prove the theorems are this proposition 3. Here, this process is the sites that are occupied by particles of type 1 at time t, beginning with this configuration of particles of type 1 and 2. And these processes are the sites that are occupied at time t by particles of type 2. Okay. This proposition says that for every finite set E, we have this inclusion. This sets here is that there are infinite times for which infinite large time for which we have particles of type 2 in 1 to infinite, that is the favorable for the particles of type 2. And we also have infinite large times for which we have particles of type 1 in minus infinite to 0. And what we prove is that if we are in this case, then there exists a time for which these two processes are equal in the set E for every time larger than this time t. And this inclusion is almost surely. Okay. A brief see of the proof. We are in the case. We are in this sets. Then there are infinite large time for which we have a site here that is occupied by this process, by the process with initial configuration AB. Then there are a lot of red points here. And for each of these red points, we have positive probability of constructing an infinite renormalized path. Okay, there is a positive probability that these points are expanding to the right. Then using the Markov property, we have that except for a set with probability smaller than epsilon, we will find a point that is expanding to the right before a large time m, and we will find a point expanding to the right in the favorable environment for the particles of type 2, and with the same argument, we also find a particle that is expanding to the left and expanding to the left in the favorable environment for the particles of type 1, and is occupied by a particle of type 1 for this process. Okay. Then once we have this, after this time m, we are going to search for a rectangle for the following event. We are going to search with for a rectangle that has height k, height n, and from minus m linear line to m line. Doesn't matter who is m line, but it's a constant. And what we want in this rectangle is that every side is has a cross mark in the Harris construction, and there are no arrows of infection coming out for any of these sides. This event has positive probability, and therefore after this time I'm going to search the first time that we have this event, that is the distribution is geometric. Then once we have this rectangle, using lemma 1 for Mumford suite renormalization, we can find these two renormalized path. One, this renormalized path is to the right of a line with negative inclination, and it ends in the right of the corner of my rectangle, and here the renormalized path is to the right of a line with negative inclination and ends in the left corner of my gray rectangle. Okay, and this happened by lemma 1. This happened with probability larger than 1 minus epsilon. Then what we have here is, if we take, I'm going to call Z the event, the set, the union of all these renormalized boxes, this one, and this one. I'm not using these renormalized boxes here and these renormalized box here. I'm only using the ones before the after the intersection of the two renormalized paths, the one coming from the expanding to the left and the one coming from lemma 1. Then what happened here in this set Z, for suppose we take a point here in Z, and this point is connected with Z. There exists a path that ends in this point, and what we have is, but the Mumford suite renormalization, we can connect this point using all the renormalized boxes to the base of this renormalized box. But since this point is expanding to the right, then we can connect this path with this point that is expanding to the left, and this point is occupied by particles of type 1 for this process by the construction. Then this point in C is occupied by particles of type 1 for the process with initial configuration AB. And we can construct another path using the other renormalized path, and we can connect this point that is occupied by particles of type 1 for this process. We can connect with this one with a path that is always in the favorable environment for the particles of type 1, and therefore the point that we take in Z, it has a particles of type 1 for one process and for the other, and they are equal in the set C. The same happens if we take a point here. Any point here going to be red. It changed the color, but here is blue, and in the red structure, everything going to be red. But the important thing is that both processes are equal in C. Then in the set with light yellow, that is a light yellow, we call this set by IZ as interior of the set C, and any path that ends in the set IZ is going to cut the set C, because the set C is connected. This rectangle is also in the set C. Okay, then the set C is a connected set, and it has width at least 2R, by the construction of every renormalized box of Mumford-Sweet renormalization. And therefore, every path in the hardest construction must cut the structure C from this rectangle, this gray rectangle, because the construction of the rectangle is that there are no arrows coming out from the rectangle, and all sides has a cross mark. Therefore, there are no paths like this. And in the other parts of the set C, we know that these two processes are equal. Therefore, they are equal in IC. The final step to get the proposition is to take T large enough such that E times T is inside IC. Okay? Okay, the sketch of the proof of theorem 1. Now we take a configuration that have infinite particles of type 1 in minus infinite to 0, and infinite particles of type 2 in 1 to infinite. Okay, since there are infinite particles of the right type in the right environment, then there exists there will be always particles of type 2 in the right environment and the particles of type 1 in the right environment with probability 1. Okay, and then by proposition 3 we will find with probability 1 we will find this time such that these two processes are equal in E. In theorem 1, what we want to prove is that this limit is equal to nu f. Okay, for every finite dimensional set. Let us prove that. What we do now is that first, with corollary 1, we know that the measure nu is supported in the configurations with infinite particles of type 1 and infinite particles of type 2 in the right environment. Here, the quality is easy to see because nu is supported in this configuration. Next, what we do is by proposition 3, we know that these events have probability 1 for every configuration in A. Therefore, this probability are equal to this probability. I'm not doing nothing. Now I change limit with integral by the dominant convergence theorem, since we are integrating a probability. After that, here, what I'm doing is changing this process by this process because I'm in this event. So that there are equals in E, and E is the set of sites on which F depends. Then I can change one process for the other. And finally, I don't know. And now I use the dominant convergence theorem to exchange limit with integral again. And after that, I use proposition 3 to go back to this probability. Since this event has probability 1, then we have that these two probabilities are equal. And here, this is equal to nu in F because it's nu is an invariant measure. And then we obtain this limit. Okay, that's the proof of theorem 1. Theorem 2. In theorem 2, what we want to prove is that every invariant measure is a convex combination of 4 measures. The trivial invariant measure, the the delta of empty set, the measure me1, the measure me2, and nu. I'm going to give the cases. If there are, this tau is the time of extinction of a particle of type 1. And this is the time of extinction of the particles of type 2. And then if there are no particles of any kind, then the process is converging to the trivial invariant measure. Okay. This is the first case. The second case is, suppose that we have, for all times, we have particles of type 1, but there are no particles of type 2. Then all particles of there exists a time for which there are, from this time, after this time, there are no particles of type 2. And the particles of type 1 are in the environment, then it behaves as the classic contract process, and then the convergence will be to the non-trivial invariant measure for the classic contract process, supported in the configuration that don't have particles of type 2. The other case is the same. If the particles of type 1 dies out, but there are particles of type 2 for all times, then it behaves as the classic contract process, but supported in the configurations where there are no particles of type 1, and the convergence will be to the non-trivial invariant measure of the contract process supported in the configuration with no particles of type 1. Okay. Another case is when now suppose that there are always particles of type 1 and particles of type 2. But suppose that there exists a time for which, after this time, there are no particles of type 2 in 1 to infinite. Then, in this case, we are in the presence of the Grass-Bush's tree process. Because there are no particles of type 2 in the environment favorable for them, then the particles of type 1 they rules in all the environment. Then the particles of type 1 will be the trees, the particles of type 2 will be the bushes, and by the article of Durat and Swindler, they prove that the Grass-Bush's trees converge to the non-trivial invariant measure supported in the configurations where there are no particles of type 2. And this is what we use here. The same thing happens if there exists a time for which there are no particles of type 1 in the favorable environments for the particles of type 1. Then, in this case, after this time, the particles of type 2 are the trees in the environment, and the particles of type 1 are the bushes. Then we are in the Grass-Bush's tree process, and the process converges to the non-trivial invariant measure supported in the configuration with no particles of type 1. The two gains all the space. And finally, suppose that for infinite large times, there are particles of type 1 in minus infinity to 0 and particles of type 2 in 1 to infinity. Then, in this case, by Preposition 3, we have that there exists a time t such that these two processes are equal in E for all time larger than this time. And since this process in Theorem 1, we proved that converges to nu, then the process with initial configuration AB will be converged to the measure nu, and we have this limit. Okay. Therefore, we have proved this equality. We have here a convex combination, what we want, a convex combination where the constant don't depends on F, and it's a convex combination of these four measures, and we have proved theorem 2. That will be all. Thank you very much.
Thank you, Mariela. Anyone have any question? Please, you can turn on your microphone and ask.
Yeah, yes, I have one question. Can you say something about the boundary? I mean, I guess you have a boundary in the new measure.
In the new measure, no.
Yeah. So in that measure, can you say something about the? I mean, is it the case that you have a sort of clear-cut boundary there, and can you say something about it? How does it behave? And
no, I don't have think about a boundary. You said a boundary?
I mean, yes, because you have a separation, right, between the ones and twos.
Okay. No, I don't know anything about this. No, this is a good, excellent question, because by what I prove is that the rightmost one is type for the process with full occupancy. Then and from this rightmost one to the right of this rightmost one, all the particles will be 2. Then I have a clear space here between the ones and the 2. But I don't know exactly. It will be a good problem to solve. I don't know nothing about that, but it should be good to think about it.
Okay, thank you.
Anyone have any other question?
So I could ask another one. so what if you have favorable preferences which are not which are not
deterministic?
No. It could be deterministic, but not not a right in the middle of the. So suppose you have 3 or 4 different alternating regions where you have preferences, things like that. I mean, could you say something for some situation like that where it's not, because I guess you separated your space right in the middle, right? And
yes,
to
right in the middle.
Have a preference for one and to the right for another. What of other? Is it possible that you can apply something like your techniques to?
I think it will be possible. I think to apply this Mumford-Sweet renormalization and get something. But I should think about it. I don't know what happens exactly, but I think it is possible to get something using for some deterministic arrange. Maybe
okay.
it will be possible, I think.
Okay, thank you very much. Now I stop. I have a question, and I think it's a very simple one. Why do you have this? Why do you choose to use this R, like the range of interaction of your contact process, and don't use the R equal to 1 as usual? Is this important?
R equal 1. Yes, it is very, very important, because it is more difficult to deal with a range larger than 1, because when you are in range larger than 2, the path can cross, but they do not intersect. And this property that every path that cross but intersects in time one, this property get the things more easy. I have to translate to the cross path using the Mumford-Sweet renormalization. I have to use the Mumford-Sweet renormalization to gain the property of the path crossing in the range larger than 2. With a range equal 1, the things is more easy, because if you have if the paths cross, they must intersect. That's that's why.
Okay.
But here, maybe an arrow can cross and they don't intersect. The path don't intersect.
They can cross without coupling. This is what I mean, right?
Yes, this is what I mean. Yes, thank you.
Okay, if we don't have any more questions.
Can I ask one, Aline?
Yeah, sure.
Oh, thanks. So I'm not sure I understood the answer to Luis Renato's first question, but in this new measure, new, it is true that there is a leftmost 2 and a rightmost 1, right?
Yes, it is.
Okay. Yeah, so that's one thing I wanted to know. Another thing, can you prove that if you start from any initial configuration AB, so with ones in A and 2s in B, that you converge in distribution to a convex combination of these measures, of these formats?
Yes, this is my second theorem. If
but the second theorem is just that any stationary distribution is a convex combination of the 4, right?
Okay. But what I'm proving is that I'm if I take with any initial sets A and B, I converge. The process converge with to a convex combination of these 4 measures.
Oh, okay.
That's what I prove.
Okay.
I think you have a result saying that actually you couple with this all ones and all 2 configurations, no? This is what maybe is the answer for his question. I'm not sure.
Well, but it could be, I think, if you start with, let's say, finitely many 1s and infinitely many 2s, then it could be that the 1s just die and the 2s take over everywhere.
Yes, that's a possibility. If they dies out, then you will converge to the non-trivial invariant measure with all particles are 2. If they survive, but they survive in the wrong environment, then you will converge also to the non-trivial invariant measure, because you are seeing the grass bushes trees. But if the one survives in the right environment, then you will converge to nu. That's the possibilities. For the possibilities to the convergence.
Yeah. All right, nice, thank you.
If you don't have any other questions or comments, let's thank Mariela again, please. You can turn on your microphones, maybe. I don't know.